All right, welcome back to the 2025 first season of the hottest seminar. Today, we're very happy to have Mario Carneiro, who's going to tell us about Lean4Lean, formalizing the meta theory of lean.
Yeah, thanks. So this is a talk that I've partially repurposed. So apologies to anyone who's seen versions of it before. So this is going to be about Lean4Lean, and I'm going to set the stage by telling you sort of about what was my master's thesis. So this would have been about 5 years ago. And it was on the type theory of lean. And so basically going to start out by explaining what lean is as a type theory, okay? And Lean, for those who don't know, is an open source interactive theorem prover developed primarily by Leonardo de Mora, formerly at Microsoft Research. Now it is developed by a whole bunch more people, and Leo de Mora is no longer at Microsoft Research. But it focuses on software verification and formalized mathematics. It's based on dependent type theory. It is let's say, a classical system. Uh, it violates the univalence axiom. You can prove false using univalence, and because it has UIP, and it's similar to the CIC axiom system or PCUIC axiom system that is used by Coq, now known as ROC. Lean3 includes a powerful meta-programming infrastructure for Lean and Lean. Lean4 includes quite a bit more than that. The mathlib library provides a broad range of pure mathematics and tools for metaprogramming, and it still does in Lean4. Now, the axioms of Lean, I'm going to introduce in stages, starting with the untyped lambda calculus. So here, hopefully, people are relatively familiar with untyped lambda calculus here. So we have expressions can be variables or applications um, or lambdas, and the lambda binds E in this expression. You can reduce either on the left or the right side of any application, and this here is beta reduction. So you have a lambda applied to an expression, and you perform a substitution in this expression. And this is sort of a reduction system, and it does lots of interesting things. So this was originally developed by Alonzo Church as a simple model of computation that's equivalent in power to Turing machines. It is Turing complete. It has a primitive notion of bound variables and substitution and a non-deterministic reduction operation on terms that sort of simulates execution. Reduction has an important property for us, which is called the Church-Roster theorem. So if an expression E reduces in 0 more steps to E1 and also to E2, then there exists some E prime such that both E1 and E2 step to E prime. Now, E prime isn't exactly unique, and also there's no guarantee that these will always terminate. So this is not a strongly normalizing system, but as long as you have two paths that go off somewhere, then they can always be brought back together. So that's what Church-Roster is telling us. All right, so let's add some types. So here I'm going to add a type system, a very basic type system where we have just one type of sort of individuals and then a type of functions. So we annotate the types inside our lambdas, and we add a typing judgment. So now we can say that if we have a context here, which consists of variables having types, then we can type a variable. We can type an application when it is applied, as you would expect. And then here we're typing a lambda. So this was developed by Church also as a type system over the untyped lambda calculus. And when you add the system, you lose some terms. And in particular, you lose the terms that don't terminate. So this is now a strongly normalizing, using the rewrite system from before on these terms is strongly normalizing. All right, so we want to add dependent types. So let's replace this arrow with a dependent arrow, which I'll be writing as for all in this talk. So here, this tau is allowed to depend on x, and the rule for application is pretty much the same. We still have this function here, although now it's a dependent function, and here we have to do a substitution into the thing. And this rule is pretty much unchanged, but now both E and beta can depend on X. And we also want to have a type of types for reasons that we'll get into, I guess. So we're going to add a type of U for the universe, and it's going to classify types. So we're going to say that, this I is a U, and for all is a U, and of course, U is a U. Now, there are some issues here. Well, okay, one issue with this dependent for all, I guess I should have mentioned already, is that I said that this tau can depend on x, but if you look at the syntax of this, there's actually no place where I can put variables in. So I can't actually depend on this. So one way that I can fix that is I just sort of merge e and tau. So they're now going to be syntactically the same class of stuff. And so now instead of having a tau here, I just have another e. And my type system is what's going to help separate the expressions from the types, but now we just have one sort of class of expressions, and everything can have a type. And U and U in particular is what's going to make sure that everything, including U, has a type. And we don't really need this I anymore because it was just there to keep our types non-empty, but now we have plenty of types, so that's great. Okay, so most of the people here are probably going to be aware that there's some problems with this axiom. So Gerard managed to prove that using this axiom, you can cause an inconsistency. So a solution to this is to add a hierarchy of universes. So instead of just having U and U, you have U1 is in U2, and U2 is in U3, and so on. And now, because we have this sort of level of universes, we need to be able to handle different levels when you combine them in an operation like this. So here, the dependent for all has a type here and a type here. So both of them have levels that are associated with them. So this one's at level m and this one's at level n. And so we need to combine those somehow. So we'll take the max. We can't do anything less than the max, or otherwise we'll get a version of this coming up again. All right, so we're going to add one more feature here, which concerns the lowest universe. So in the so-called Curry-Howard correspondence, propositions act like types, and we really want to sort of lean on that here. So that's actually kind of why I use this for all to represent the dependent function type, because the arrow and the for all basically act like the logical operators arrow and for all from logic. So we can identify the lowest universe, U0, which we'll call P, as the universe of propositions. And we want things like all natural numbers are even or odd to also be propositions, but if you read the for all rule that I just gave on the previous slide, we don't really get that. So I said that when you have a dependent for all, if n is like a type, which is not a proposition, so it's living in universe 1, let's say, and even n or odd n, this is a proposition, so we're going to have it living in the universe of propositions, U0. So if we take the max of 1 and 0, we get 1. So this is not a proposition. So we don't want that in this situation. So we're actually going to adjust this rule and use, instead of max, we're going to use Imax. So Imax is impredicative max. So it's a definition here by cases, essentially. We say Imax mn is 0 if n is 0, and it's max mn otherwise. So that way, if n, that is to say the second thing here, is 0, then it's always going to be a 0, even if this thing is bigger than 0. So that ensures that this thing is going to be in U0. All right, so this is what we've got so far. And we still have some issues here. So one issue is that the types, so this is like the identity function applied to tau, and tau are not the same, even though one of them reduces to the other. We have this reduction system, but it's somehow not being utilized. And so if we have something that has this type and we need something of that type, then they're not going to match up. So that's not good. So the way we solve that is we add a relation called convertibility or definitional equality, written with this triple equals here. And we'll have a rule that says when E has type alpha and beta are definitionally equal, then E also has type beta. So this is going to have some rules. These three say essentially that it's an equivalence relation on well-typed terms. And here we want to say that it sort of factors through every operation. So as long as all the pieces are definitionally equal, then so is the composed thing. So both lambda and for all have these sort of rules and application. And now we can add the beta rule here as a definitional equality. So this is what's going to allow us to resolve this this issue. So this beta reduces to that. So now these two are definitionally equal, and so we can use this rule to sort of manage any mismatches. And we're also going to add this rule. This is called the eta rule, which says that if you have a, oh, this is a typo. This should say that E has a function type, a for all type. But if E has a for all type and you sort of write a lambda and apply E, then this is the same thing as E. All right. So we also need to add more types, basically because here we just have function types more or less, and we want to have something more like data types. And so I'm going to try to describe to you a general framework for adding new inductive types. So it's not just that we want to add specific inductive, like we could just add n and sum and product and be done with it, but because we're trying to support like a general class of things, we have to describe sort of what kinds of inductive types are legal. And so we have this grammar here. K is like an inductive specification. So we have the empty list of constructors, and then we have adding one more constructor. So this is like a name, and this is an expression. So we want to say this constructor has its type E. And so list of constructors with their names and types is an inductive specification. And when you have one of those, you can perform this mu operation, and this is sort of the equivalent of like the inductive type generated by this specification. And this E here is the type of the type. So we're generating an inductive type, and this will be that inductive type's type, which will be a universe or a bunch of arrows leading to a universe. And we're going to get three things out of it. We're going to get the type itself. We're going to get a constructor corresponding to the C's that were described in the inductive specification. And then we're going to get this rec, which is a recursor. So this is helping us construct functions out of this inductive type. And so here's just some examples of how we can use this to generate a bunch of interesting types. So we can define the natural numbers to be the thing, the least sort of type T, such that 0 has type T and successor goes from T to T. Exists. Here we want to define like there exists an X such that P of X, and this constructor has basically two arguments. This is for all X of A, for all something of type PX, then T, and the arrow is just for non-dependent for all, so like for all where you don't use the argument. And so if you take the mu over that, you end up with exists. But notice that this one lives in U1 because it's a type, and this one lives in P because it's a proposition. And we can also define and or and true and or no false and true. Okay. Each inductive type comes with a constructor and a recursor. So the constructors are the things that allow us to construct the type. So here, if we had n defined like this. The two constructors that we got out of it would be, so that was applying this C construction thing. Applying it to this n, we end up with 0 and successor. And then we also get the recursor for n, which says, well, if you have a function over n producing some type in some universe, and you have a value of that at 0, and you have a value of that at successor of n, given that it's true at successor n, then you get a function over all successor n. So this is essentially exactly the principle of mathematical induction. And also you get one more thing in addition to these constants. You also get a definitional equality of this form. So when you apply a recursor to a constructor, the two reduce and you get, in this case, this variable z, or you can get s applied to the previous value n, and then also the sort of recursive call. So s is a function which takes in the n, and then also the previous cn, and the way we get that here is by applying the recursion. So this is simultaneously a definition of which gives us induction, and it also gives us the ability to define functions by recursion. Okay. So there are some restrictions on what kind of rules we're allowing as inductive specification. So one of the things that we require is that this type here has to be so-called strictly positive in this variable t. So that means that essentially t doesn't appear on the left of an arrow. So this t here is in a bad position. We need this because otherwise you can define types that violate provable theorems. That would be bad. We also allow inductive families. So I mentioned, this type here doesn't always have to be a universe. It can also be a function ending in a universe. So here we're defining EQ as a function over alpha returning a prop. And we have this lambda on the outside. So this is a parameter, and this is an index. And here we're going to say that it has one constructor ruffle, which holds a t of this x out here. So then that means that ruffle is an equality of x to x, and then we end up with this, which you might know as the J rule. So we also want this property proof of relevance, and this is where we basically lose out on the hot interpretations. So we want to treat all proofs of a proposition as the same. And formally what that means is that if we have P whose type is prop, and we have H and H prime whose type is P, then H and H prime are definitionally equal. So yeah, this means that equality has at most one proof. And we do have to restrict some inductive types that eliminate. So here exists is an example where it has a type which is prop, and its recursor, normally recursors will have a type here which is just an arbitrary universe unrelated to the universe in which this inductive type itself was defined in. This is part of the reason why you can't define these inductive types as sort of imperative encodings for people who know what that is. So here we actually have a type at a fixed universe, but it eliminates into arbitrary universes. But in this particular case, because we have a prop here, and because props have this property of proof of relevance, we actually need to restrict this to U0, that is P. So rather than just U anything, which is what you normally get from a inductive type. All right, so, but there are some exceptions. So there are some inductive types which live in P, but still eliminate into other universes. An example of that would be equality. Where am I? Yeah. So roughly speaking, the rules are some kind of syntactic approximation of having at most one inhabitant by definition. And so we call this subsingleton elimination when this occurs. On top of all of this, we have some actual axioms. That is to say, these are introduced with like an axiom keyword after setting up the core inference rules of the system. One of them is propositional extensionality, which you can also think of as univalence for propositions. So if you have two propositions and they are, and you have an if and only if between them, then they're equal. There's a question. Sorry, I missed that there was a question. Emily, did you want to ask it again or?
No, that's okay. We can, yeah, so sometimes we use the chat so the peanut gallery can talk. So feel free to ignore.
Okay.
We'll discuss at the end.
Okay.
But folks can interrupt if there's a question that would help.
Yeah, that's probably a better
understand.
idea. Yeah. Okay. So quotient types are introduced. It's kind of similar in some ways to the introduction of inductive types in that we add a bunch of constants and then add some definitional equalities. But for technical reasons, these are added as axioms, and then this is added sort of by magic. So we introduce a constant quot. So this is you give it a type and a relation on that type, and it gives you another type. And then it has a constructor called make, an eliminator called lift, well, this is essentially the higher constructor of the quote. It says that if you have a relation, then make of the two is equal. And then you have this definitional rule, which says that lift applied to make reduces. So this, for people who know hot, this is basically a higher inductive type, and I don't think that there's anything too special about it beyond the fact that our inductive schema doesn't allow us to define higher inductive types. So we have one very specific higher inductive type, which is just axiomatized in this way. And then the axiom of choice, which is stated basically like this. So we can define non-empty as a inductive type where we just have one constructor called given an element of alpha, but it lives in prop, and this thing does not have the subsingleton elimination principle. So it's sort of the propositional truncation of alpha. You can think of that. And choice is given an element of non-empty alpha, we get an alpha. And there's no truncation or anything. This is just global choice, okay? And that's the axiom of choice. And now, so that finishes it for what Lean, the system is, essentially. All right, so what are some properties? So one pretty important property is that this type system is not decidable. So I say it's almost decidable. There's basically a really weird edge case where you can get the definitional equality to run off and do things. This does not really happen in practice, and actually Lean will not do this running off process. It will just approximate, it will not implement other aspects of the definitional equality when you get close to this sort of thing. I can give you the sort of gist of the issue. So it's basically a interaction between subsingleton elimination and proof relevance. So to demonstrate, I'm gonna declare this this type ACK. So ACK is an inductive type. It has one constructor, and this stands for like accessible. So we're saying that something is accessible with respect to some relation if all things less than that value are under this relation are also accessible. So for instance, if this was like less than on the natural numbers, then 0 is accessible because nothing is less than it. 1 is accessible because the only thing less than it is 0, and that's accessible. And 2 is less than is also accessible, and so on. And in fact, we can use this to define what it means for a type to be well founded by an order. Yeah, so what makes this particular type interesting is that this type is a subsingleton eliminator. It matches the sort of syntactic checks that allow Lean to say, yes, this is allowed to eliminate into larger types. But it's also recursive, so that's Interesting. Um, we can define an inverse to this intro. So inv is gonna, given an x and then some y which is less than x, y which is less than x, it'll give us an y. And so basically this for all here is exactly what we need to pass in to this argument here. So that means that we can write intro x of inv x of a, and this is going to be definitionally equal to a just because these two have the same type. Like if you just work out what the type of this is and what the type of this is, they're both going to be x, and so therefore they're definitionally equal by proof of relevance. What's the trick? Well, let's add, let's say P is some decidable proposition such that for all n, P of n is not decidable. So for instance, P of n is that a Turing machine runs for at least n steps. And now let's suppose we have some hypothesis H0, which says that 0 is accessible with the greater than relation on the natural numbers. Now, note, this is not true, right? The greater than relation on the natural numbers is not well-founded, but we can have it in our local context regardless. So let's just say we have this thing in the context. And with it, we can define a function which maps anything inside ACX. And again, ACK is empty, but we can define it by recursion on this ACK greater. So basically, when we do recursion on an element of this thing, we're allowed to assume that something is true for all the values greater than it. And so we can essentially do recursion up the natural numbers. So this is where things sort of get funny, right? So we're going to say f at n is going to be, if p of n, then, well, we call f at n plus 1. And we use this inv thing in order to get a proof that that the next value is still greater than well-founded. So using greater than well-founded at 0, we can deduce using inv that it's greater than well-founded at 1, and so on. So this allows us to do the next call. Otherwise, it's going to reduce to 0. And p is just a proof that n plus 1 is greater than n. So under that context, if we use this h0, f of 0 at h0 is definitionally equal to 0. This definitional equality problem is derivable, it's provable, if and only if for all n, p of n is false. That's a typo. Basically, in order to deduce whether or not this definitional equality holds, you have to unfold f using accessibility recursion, and if at some point this Turing machine halts, then the whole thing reduces to 0. Otherwise, it just keeps being f of other things, and so the definitional equality doesn't hold. So what actually happens? Well, Lean will underapproximate the definitional equality and the typing judgment. And so we can introduce some notation, this like back arrow and double turnstile for the thing that Lean does. This is some kind of under approximation. So this implies the real typing judgment, and this implies the real definitional equality. Although this is going to be decidable, it's not going to have all the properties that we want from the original. And in particular, it's not going to be transitive. And this typing relation is not going to satisfy subject reduction. So subject reduction is that if you do a reduction somewhere in the middle of a term, which is well typed, that it will stay well typed. And it's easy to construct from non-transitivity. Just apply different versions of the identity function. And if you reduce some of them, you can basically test whether transitivity holds some triple of types. So these two are basically the same. And as I said, this issue is extremely rare in practice, and it can be circumvented by inserting some identity functions. You actually sometimes want to do this anyway, even if you did have a decidable typing judgment just because it's decidable doesn't mean that it's fast. Like you might have a situation where doing subject reduction just makes a lot of things more expensive. So that can be an issue. But okay, so there's an obvious model of this theory in ZFC, where we treat types as sets and elements as elements. This is actually one of the things that I like the most about Lean's type theory, that it just has the natural model and it works. So I think I'm gonna skip the details of this, but you can basically construct some model where you use ZFC plus omega inaccessible cardinal. So you're going to use an inaccessible cardinal to interpret each of the UNs, and then they lie in some kind of increasing hierarchy. And these are the main theorems. So if you have k inaccessible cardinals, then you can actually interpret, well, you can interpret every typing judgment with some finite number of inaccessible cardinals. So this proves the equiconsistency of Lean with ZFC and this infinite sequence of axioms. There are n inaccessibles for all n less than omega. And as a consequence, Lean is consistent. There's no derivation of false. That's great. So the soundness theorem depends on this sort of syntactic technical thing called unique typing. So we use this function. The reason for this is we use this function level that sort of given an expression, or sorry, given a type variable or a type expression in some context, it will tell us the n for which alpha has type un. For this to be well defined, we can't have alpha be in un and also in um for some different m. So we need to have these two properties. One of them is unique typing. So that is to say, if an expression E has two different types, alpha and beta, then alpha and beta are definitionally equal. And it needs to have these properties here called definitional inversion. So if two universes are definitionally equal, then m equals n. And then similarly for alls, and you also need to be able to distinguish for alls and universes. So these all feel very obvious. I mean, all four of them, I would say. But proving them is actually quite technical and difficult. So this isn't exactly true in Coq because there's universe cumulativity. So like this rule here is just not true. You can, or at least there's a subtyping relation instead of just a typing relation, and m might be less equal to n, and then this here has to be written in a different way with principal types and so on. So there's something like unique typing, but it can't be stated quite in this way. Okay, and I'll skip the details of the proof. And I mentioned, okay, so one of the interesting middle points of this proof is the Church-Rosser theorem for this typing system. So if E has one type and that type reduces to two different types, then they come back together. Now, this doesn't quite look like the original Church-Rosser theorem for untyped lambda calculus. In particular, they don't actually quite come back together. They sort of come back together modulo some equivalence. This equivalence is a fairly syntactic check on sort of being equal except at proof arguments. So like if you have two proofs of a proposition P, then they're just automatically P equal, even if they have completely different structure. But other than that, there are not a lot of, the rules are essentially just the structural ones. So if the pieces are equal P, then so is the main thing. And then also this is for eta equality. So you can unpeel a lambda on one side, and there's a symmetric version of this. Okay, so this is where my work 5 years ago ended. So I, dreamed about maybe we can have more model theory of lean, figure out how the evaluation model relates to lean reduction, and prove strong normalizations, and of course, formalize the present results in lean. So 5 years later, I came back to this project. That's a couple months ago, well, maybe a year ago. So the paper that I wrote, this master's thesis, is now sort of a standard reference for Lean TT, which is nice. The model theory of Lean is still not formalized, but the main results of it are more or less common knowledge in the sort of Zulp discussions and so on. VM reduction is still open, but there is some work on proving properties of VM reduction in Coq, and so I have hopes that those will transfer to Lean. Strong normalization has been disproved. So there was a example where you can get, using some tricks that are not too dissimilar from this ACK reduction business that I showed, you can also get untyped lambda calculus essentially to occur inside reduction in proofs. So what, of course, I want to get to is that all of these results, well, there is work on proving the results that I've discussed in Lean, and that's what Lean4Lean is. So what's the deal? So Lean is about 80% written in Lean. So that means the parser, the elaborator, the tactic language, the metaprogramming framework, even the LSP server, they're all written in Lean. This is not the case in Lean 3, but it definitely is the case in Lean 4. There are a few exceptions. The runtime, which is very small, that is to say the thing that sort of makes Lean code actually go. That is written in C, and it just sort of interfaces with the operating system. The interpreter, so you can run Lean code sort of without compiling it, and that uses an optimized interpreter, which uses some tricks, which would be somewhat difficult to do in Lean. About half of the back end of the old compiler for historical reasons, and the kernel. And I would say that one of these is not quite the same as the others. It's both mathematically interesting and soundness critical. So I think we should rewrite that part in Lean. So the project goal here is to write a Lean kernel, which is complete for everything the original can handle and competitive for the original, so that it can be seriously considered as a replacement. The second part is to write down the type theory of Lean, but formally this time, in Lean itself, to prove structural properties of the type system and to prove the correctness of the implementation with respect to the specification. So I want to prove that a real kernel implements the real type theory, and that the real type theory has the properties that it has, and the non-properties that it has too. In particular, one of the properties that it should have is soundness. I really want to prove that one. So what's the status of these things? Kernel, check. Complete, check. And competitive, check. I'll show you that. The type theory is also written down. I'll tell you some more about that. Some of the structural properties have been proved, others are in progress. Correctness of the implementation is still just in the planning stages. All right, so the Lean4Lean kernel itself is basically a carbon copy of the C++ code. It does all of the same fancy tricks as the original, and it does not implement the fancy tricks that have been proposed to replace the original, because actually the original is somewhat slow in very specific ways, and we could definitely be doing better, but I hope that having this thing implemented and proved correct will be a good testbed for being able to make changes to the kernel without fear of breaking things. So like the current version of the kernel, people are very scared to touch it because they don't want to introduce soundness bugs, and I think that that's a very reasonable thing. So it has like union find for caching, it has pointer equality testing stuff, it has bidirectional type checking tricks, it does some heuristics on definitional equality, which are very important and cannot be implemented differently without causing some weird edge case in mathlib to go running off somewhere. It has edit for structures, it has nested inductive types. These are new features since Lean 3, and Lean4Lean implements them. I have an X here for a naive implementation of substitution or reduction. That is to say, it is exactly as naive as the original implementation. There are much better ways to implement this, but those are sort of plans. I think it's sort of suitable for differential fuzzing. That is to say, it gets, you can count exactly how many times a given definition is unfolded and so on, and you'll see exactly the same numbers for running Lean4Lean versus the original Lean kernel. It uses Lean's own expert type. So when some algorithms are available already in Lean code, they were reused. But other than that, for the most part, it's all new code that was written in Lean for this project. One of the unexpected benefits of doing this was that people immediately started hacking on this. Like David Renshaw showed this visualizing reduction. So like reduction sequences that actually occur in the kernel are somewhat opaque. Normally, the original kernel was not written to make this sort of information available, but because Lean is sort of easily moddable, he got a version where this was being shown in some widgets, and it's quite fun to see people making use of it for this sort of thing. Rishikesh Vaishnav showed this extension of Lean4Lean called Lean4Less, which was doing elimination of definitional equality, sort of bringing Lean closer to a what's it called? A type theory. I can't remember the name. A type theory where you don't have definitional equality at all, and you just rewrite instead. And yeah, and this is because Lean is just less scary than C++ for experimentation, at least for people who are used to using Lean. So here's some benchmark numbers. So performance is a bit worse. I do hope that improvements to the compiler, the Lean compiler, will improve these numbers somewhat. I would say that, 30% worse is not bad. Like, you can absolutely make use of that. It's not like 10x worse or something like that. Lean itself took some hits at a similar order of magnitude when it moved the elaborator out of C++, and then it clawed back all of that performance and then some by implementing just better algorithms. And I'm pretty sure that the same situation will occur here. That like having this as something written in Lean is going to make it easier, especially once we have these theorems, is going to make it easier for people to be able to make modifications and not be so worried about breaking things. And yeah, that's basically what I said. All right, so back to type theory of Lean. So these are the rules sort of as they actually exist. Now these are the LaTeX versions of the inductive type for the definitional equality and typing judgments. So there are some changes. So here I have a definition, just what is lookup in a context. And here we have the definition, which is sort of combined of both definitional equality and typing. So the idea is, well, when the two things are the same, we're going to treat it as a typing judgment. So we're just going to say, when you can prove this thing, then we'll just write it in the cell, and it's a typing. And if they're different, then it's a definitional equality judgment, but it's a typed definitional equality. We're going to say that both sides have this type alpha that's the same. Okay, so This is how you get variables. You can do symmetry, you can do transitivity. The transitivity does require that the types be the same sorts. So this is if you have two universes, then you do congruence, and it also tells you the sort of a universe. This is for looking up a constant in the environment. So E here is the environment. And then there's some checking that the universe levels here are okay and that they're definitionally equal. So this is basically what you need to do in order to apply a constant from the environment, because environments are actually universe parametric, and so you need to apply them at some universe levels. And this is the rule for lambdas. There's some more rules. So this is the rule for all. We can see this Imax comes back, but otherwise this is pretty much the same as what we saw before. Application, here's how when you apply a function at a for all at some value, you substitute one side. You'll notice here that there's E2 that's being used, but there's a lemma that, well, you can replace it with E2 prime, and because those are actually definitionally equal. This is the conversion rule. It looks a little bit funny because we're doing the conversion rule in a conversion rule. So these are E and E prime at some alpha, and I want to have E and E prime at some beta, but alpha and beta are definitionally equal. This is the beta rule. This is the eta rule. Here's proof of relevance. And then this is the extra rule. Now this is sort of a cop-out. There's a definitional equality in the environment. So the idea is that this environment keeps track of definitional equalities that you're just allowed to instantiate. And so, for instance, if you have a definition, you're going to have the constant. So like this rule here is used for the constant, but there's also going to be another rule, which is a definitional equality, saying that the constant is definitionally equal to its own definition. So both of those things get added to the environment. When you add an inductive type to the environment, you add constants for all of the types and recursors and so on, and then you add definitional equalities for the iota rule. So there's going to be some specific rules on what you can add to this environment, but at this point, we just sort of take whatever's in there and say those definitional qualities we're allowed to use. All right. So I said this, and also the original definitional quality, which doesn't have an alpha, we can just define that by saying, well, there exists an alpha such that this typing rule holds. All right. So boring rules. If you have a typing judgment, then E prime, and alpha are well scoped. And I think you also have to assume that gamma is well scoped in this statement. Let's see, you can insert delta between two, so you can add some weakening in the middle of a local context. This rule says that you can do universe substitutions. This rule says you can do expression substitutions. And this rule says that you can do substitution, you can do sort of definitional equality changes, but in the local context, at least at one level. And there are also, so these are weak inversion rules. I'll get to what a strong inversion rule looks like, but this one says, if you can prove that a for all has any type at all, I don't care, then alpha must be a type and beta must be a type. And by the way, this type just means alpha colon UL for some L. And similarly for lambda, like if, you know, these two expressions in here, if you could type this lambda, this whole lambda, then you must have at some point in the typing derivation also typed alpha and E. So that's how I can derive that alpha and E have these properties, and so on. Another one is that types are typed. So if E has type alpha, then alpha has type UL for some L. And substitution. This gets a little complicated because even knowing that these have the same type requires this very theorem. So you have to apply the theorem to itself, and then it stabilizes after 2 iterations. But we also have some non-theorems, or at least theorems that turned out not to work. So the unique typing theorem, I have not disproved it, and I still believe it to be true, but the proof had a gap. So there is an alternative path to the proof of soundness that skips this, but there are some kernel optimizations that definitely depend on this theorem being true. So this is an area which I'm still looking into, and it is one of the things which at the end of the talk, I'm going to ask for people to help me out with. Yeah, if you ask questions, I can tell you more about what's interesting in this, in the original proof and what's been going on. Okay. And both of these two theorems got implicated because they're actually proved mutually recursively. So you need this stuff in order to prove bits of this, and then you need this in order to prove bits of that. So it's a very sad situation. Okay, so there are some recent results which sort of lead up to that main theorem. The main proof structure of this theorem does still seem to hold. There are some details involving the way in which you do the induction, which don't quite work out. So here are some lemmas that lead you towards church roster, and church roster is really the key here. Once you have this property, like getting definitional inversion is easy. So like if you have, let's see, so suppose you had a definitional equality like this, then you could do reduction here to go somewhere, and then here to go somewhere else. And those somewhere else will end up being, they will have this equal p relation. That's essentially what this last rule says, right? If two things are definitionally equal, then they reduce to something where they're p equal. And when they're p equal, you can just read off that, well, that this holds and that this holds, because these two are not p equal. Like, just syntactically, it's impossible for it to happen. So that's sort of how this proof goes. Yeah, so the proof involves showing that this thing is an equivalence relation, that you have this, this is called parallel reduction, and the other one is called complete parallel reduction. So this is a sort of deterministic version of this relation, and so you get these lemmas. I'll show you more if you're interested. But okay. So the inductive types have all been stuffed into this sort of T extra rule, as I mentioned. I've been experimenting with different ways to express the rules for inductives because it's kind of a pain to describe what the inductive schema is otherwise. I had some success with using a sort of pattern language to specify the rewrite rules. So the idea here is that this is a pattern. It's either a constant or an application or a thing applied to a variable. So the variables only occur on the right side. And then this is a sort of a right-hand side of a pattern, which will be either an expression with an explicit substitution of some levels, or an application, or one of the named variables that, or numbered variables, I guess, that appear on the left-hand side. And then there's some predicates which are guards on the condition. So we can only apply the pattern when certain definitional qualities hold. This is actually somewhat difficult for some, like when you try to encode Lean in Deducti, this is annoying, but this is just how some rewrite rules have to work. So like Axiom K checks the types of things, and if the types are not definitionally equal, then it will not reduce. So here's an example of here's the pattern reduction rule. So if you have a pattern, So P goes to R if psi is true, and E is a sort of application of the pattern at some sigma, and then when you apply this thing at sigma, it's true. Then you can reduce. So sigma I believe, is well, sigma I is one of the pieces of this reduction. So this is I guess this is parallel reduction. This is how this works. So like R is the result of applying this reduction. This is a somewhat high order sort of way of describing what a rule could be, but the point is that this can subsume rules like this. Like this is what showed up in the 5 years ago paper, and this is just a whole pain to work with as a single inductive rule. So this is simplifying what it means to do that kind of reduction. Especially because this shows up like this is in complete reduction. It also appears in parallel reduction and also in standard, just the squiggle arrow reduction, and then definitional equality. So like not having to reproduce all of these details of what's a subsingleton inductive and what is all this in stuff and so on. All right, so summary. You can use Lean4Lean now as a replacement for Lean's kernel if you want. The formalization is under active development, and if any of you are interested in proving type theory kind of stuff about Lean, I would really appreciate the help. This is definitely not a one-man project, but I am one man. And not all of the mathematical problems are solved yet. This is still there is still some interesting research to be done. Confluence in general is a hard problem in dependent type theory, and well, yeah, Coq and Agda both have to handle this at some level, but they are sort of postponing it. And in Lean, we really have to deal with this problem. This is like core to how Lean works. But yeah, there are not enough type theorists involved in Lean, so if you self-identify as a type theorist, maybe come help out. Okay, thank you.
Great. Thanks very much. So we traditionally offer some silent applause, so we'll do that. And then open the floor for questions. So feel free to unmute yourself or raise your hand or type something in the chat, whatever is most comfortable.
Mario, can I ask you a question?
Please do.
So when you were describing the definition of the Lean type theory in Lean, on your slides, you were kind to us and used what I would say was a nominal representation. You actually used named variables, but I'm guessing you don't actually do that in the Lean code.
Yeah,
or
that's correct.
what representation do you actually use?
So that's a little complicated. So there's actually two versions of expression representation in Lean4Lean. One of them is for this kind of stuff, the type theory part. The other one is for the kernel. So the kernel is implemented, as I mentioned, in a very similar way to Lean's kernel, and it uses the same tricks that Lean does, and in particular, it's using locally nameless representation for its binders. So it will use these globally
That's very
unique
good.
FVARs
That's the right
for
answer.
gamma and bound variables inside the things. And so I do like locally nameless. I think it's very good for writing tactics and so on. But that is not what I use for the type theory. For the type theory, I'm using pure de Bruijn. And the idea is that this simplifies a lot of the reasoning about these sort of things. With locally nameless, you have to keep track of these global names that you sort of assign, and so it's a much more stateful approach to things. So the idea is during the verification, there will be a proof that locally nameless is isomorphic to pure de Bruijn, but all the theorems get proved on that pure de Bruijn version.
Okay, thanks.
So I have a much more naive question just to make sure I understand the project. So, in Lean4Lean, you are both, describing the type theory of Lean in Lean, but also describing the kernel. The kernel is rewriting the kernel so that is also in Lean. And then the idea is that you can prove in Lean that the kernel as implemented is reflecting the rules of the type theory, and then also
Precisely.
some meta-theoretic theorems about the type theory. One of the motivations, I feel like that motivates itself, but an additional motivation would be, you said if somebody wanted to make a tweak to the Lean implementation of the kernel, then there would sort of be more confidence there, but presumably tweaking the Lean implementation of the kernel would require then completely new proofs that the kernel is still and correct implementation. Is that?
Yes,
Is
that
the
is
idea?
correct. Yeah. I think of that more as a strength than a weakness, but it's absolutely true that like it would make on like a literal technical level, it would make it harder to make changes, right? The point is that it makes it easier to make correct changes. Like right now, making correct changes requires a PhD, and it would be nice to make it such that at least Lean will tell you when you got it right. Yeah.
Great. Yeah, that's a useful clarification. So you're sort of raising the obligation, but requiring less, I guess, in terms of the expertise of the program developer or whomever.
Yeah.
I have another question, if nobody else does. I was kind of actually surprised to see confluence being mentioned at all. So you're making a specific choice there, and probably for a very good reason, I guess. But I mean, there are other, as I'm sure you're aware, other ways of doing things that, in a sense, don't require you to think about confluence whatsoever. But I mean, in particular, you could have a typed notion of reduction there are routes to the results that you ultimately want to prove about the meta-theoretic properties of this type system that don't go via actually proving confluence, but go by other ways.
What I would say is that's very interesting. You should come talk to me. I guess I've seen a lot of ways of proving this kind of thing that go via properties that I know not to be true. In particular, strong normalization, like logical relations, proofs of properties of definitional equality almost always a fortiori imply strong normalization. And as a result, I just know they're not going to apply. Like unless I find some way of modifying
Well,
the
hang on a
system.
moment, just a moment. I mean, but that presupposes that you have a notion of normalization, let alone a strong one.
Well, it's true. Like actually,
I
as
mean,
I
so you
introduced
can have
this definitional
reduction-free
equality.
proofs I mean, yeah.
Yeah.
Fortunately, I mean, where you are, you're surrounded by experts on this kind of thing who you can go talk to, right?
Yeah. The definitional equality, as I introduced it, doesn't have a reduction system built in, right? This.
Yeah, that's kind of what I'm. Well, that's what
Yeah.
I'm hinting at. Yeah.
Like here, it doesn't say anything. Like it doesn't say that you have to use this left to right. Like you could do it backwards if you wanted, right?
Yeah.
But this proof of it does go via, like, we actually introduce a reduction relation. In fact, it's a really bad reduction relation, which you would not want to use for other purposes, but it is a reduction relation which happens to satisfy these properties. And so this is a proof technique, right? Like using all of these relations in order to prove some kind of confluence-like result. To be perfectly honest with you, I don't know any other way to prove this result. And I mean, this way, as I mentioned, also is, suspect. So if you have ideas, I'm absolutely, ears open, wanting to hear it.
I think the problem is that one always has ideas, but the proof is in the details, right? So
Yes.
I can't say to you, oh, just don't do that, because
Yeah.
I mean, my own personal experience is that whilst in principle you might think that you can prove something, but when you get down and dirty to the actual details, right? I mean, there may be only one way that one can think of doing the thing. So I'm just interested to see it. I'm not saying that you shouldn't be doing it or anything.
Yeah.
Yeah.
Yeah, and I mean, I should mention that like this theorem, this was like revision 10. I went through so many failed versions of this proof before I got to this version, and it turns out this version's also failed, although I found it out many years later.
Yeah, I mean, the
So
injectivity of pi types is a very annoying thing that
mhm,
one would like to really have proofs of meta-theoretic properties that don't use that property, because it's mathematically speaking, it's so unbelievable.
mhm.
I mean, it doesn't hold in most models, as it were.
Well, it model it.
But most of the proofs I know of this kind of thing that you're talking about very much do need to have that injectivity property.
I mean, this
Yeah.
injectivity holds for definitional equality. It definitely doesn't hold for equality. Like it's disprovable in Lean for equality, for
Oh yeah, sure,
propositional
yes,
equality.
yes, of course, yes,
Um,
yes, yeah.
for
So in other
definitional
words,
equality, though,
definitional equality is a very intentional notion, right?
yes, exactly. Yeah.
Yeah,
And I mean, I don't know, intuitively it feels like it should be true just because there's just so few, how could you find your way around these rules and somehow, this is the only rule which we gave you to be able to prove two things are equal. So, you play games with lambdas, but eventually you got to come back to it, right? So that's sort
yeah,
of my intuition on, why this kind of thing should be true. But then
yeah,
you have this proof of relevance, which is sort of like goes crazy with, who knows what H and H prime are. Uh, so
yeah. I
because
mean,
of all of that,
it's
there's lots of details.
yeah, yeah.
Yeah, devil's in the details, as you say.
Would you show us a little bit of the code?
Yeah. Uh, Let me see. So I prepared some stuff. Let me see if I can get it to appear on screen. Voila. Okay. So let me show you what the definitional equality judgment that I mentioned actually looks like in Lean. Let me make this a bit bigger and get rid of that. So here, so this says like, okay, if I want to define, so expressions are variables, sorts, constants, applications, lambdas, and for alls. There's a bunch of stuff about how pure de Bruijn works. So as you can see, there's only one kind of variable, and it uses a nat index. And then here we just have all of the rules which we saw in LaTeX form before. So like this is the symmetry rule, and this is the transitivity rule. And then there's constants and so on. So, and this is that extra rule that I mentioned. So here we're sort of pulling df, which is some kind of definitional equality thing, out of the environment, checking that everything is well formed, and then instantiating levels. So this is a pretty direct translation of what one would want the definition to be. And then we have a whole bunch of lemmas about like how well formedness works, how like that instantiation works, that you can apply instantiation of some expression inside another expression. The number of variables just keeps growing in these sorts of things. But they're all sort of very syntactic proofs. And this was sort of the here's where things start getting complicated, and there's sorries and whatever, because this isn't a finished proof, but here's that definition where we give a parallel reduction, and then we have complete parallel reduction, and these are the rules that define it. And this and matches thing is the pattern matching that I was describing in the talk. And Yeah, so I'm hoping that I can prove those various properties that I showed before. So this is what the theory work looks like, and then what was it? Typechecker, I think. Yeah. So this, on the other hand, is the actual kernel. This is the let's see, I can here, like this is inferring let expressions, and this is sort of very imperative code. It's got some loop. So this is some pulling off a sequence of let binders, doing some instantiations, make fresh ID, which has some named. So this is how it creates new let declarations. There's some flags and so on. So this is just a very different kind of code than this sort of pure these inductive types. And so what I would really like to prove is that this ugly code satisfies the properties, well, some kind of property that relates it to the real thing. Yeah, so that's what this looks like.
Okay, any further questions?
Oh, and I guess I should mention that, well, you can find this if you just search Lean4Lean on GitHub. You should find my project. I think I put a link to it in the talk. But yeah, if you want to help out, that's how you can do so.
Great. So let's thank Mario again with another round of silent applause. And we'll see you back in 2 weeks.